In this video, we're going to do practice for all of the counting rules that we've learned, including permutations and combinations. Let's start with some basic bit string practice and just continually get harder from there. Keep in mind a bit string, bit meaning that our values are either zeros or ones, so it's basically a binary string. So I'm looking at how many binary strings or bit strings of length 6 are there. So when I'm thinking about this, I'm really just going to use the multiplication rule that says if I have 6 different events happening, which is choosing a value of 0 or 1 6 times, I'm just going to multiply the number of options there are. So if there's 2 options, 0 or 1, and 2 options, 0 or 1, and 2 options, you get the idea. I really just have 2 options 6 times, so that is 2 to the 6th. So 2 to the 6th is the number of bit strings of length 6. Now the second question is quite a bit harder than the first one. So the first one says how many of length 6 are there? Now we're getting some other conditions. How many start with 1 or end with 1? So the or right away tells me that I'm going to have some addition. There's more than one thing happening. Now, it could be addition, just straight up addition, or it could be addition and subtraction because of the principle of inclusion-exclusion. So we have to ask ourselves, is it possible to have a bit string that both starts with 1 and ends with 1? And in this case, the answer is yes. And so because I can have elements that occur in both of my sets, I'm going to end up with subtraction as well. So let's remind ourselves of the principle of inclusion-exclusion that says if we have some set A and some set B, we're going to add those together. That's where that or comes in. But if I have any overlap, I have to take out the ones that I counted twice. So that's the principle of inclusion-exclusion. So what I need to do is basically find the number of elements in A, which we're going to say is start with 1, and the number of elements in B, that is end in 1, and then the number of elements in the intersection, which is start and end in 1. So again, we're dealing with bit strings, so we just have our 6 choices, and we have it for all 3 of those. Now for the first one, I'm going to set the 1 as the first value. But all of the rest of the values can be either 0 or 1, which means just as I did in my first example, I have 2 choices, and 2 choices, and 2 choices, and 2 choices, and 2 choices, 0 or 1 for each of those. So the number of elements in set A is 2 to the 5th. The number of elements in set B, as I'm sure you could probably guess, is going to be the same because I'm still setting just one value, and all of the rest of the values can be either 0 or 1. So that is also 2 to the 5th. Now I know that I'm looking for how many both start and end in 1. So now I'm going to set, change my color back. I'm going to set this as a 1, and I'm going to set this as a 1, but all of the rest of the values can be either 0 or 1. So that's 2 to the 4th. So in this case, I'm going to take 2 to the 5th plus 2 to the 5th minus 2 to the 4th. Now, depending on what the instructions of your question are, it might be perfectly acceptable to leave this as 2 to the 6th, or you might need to go to the next step and write it as 64. So if you're taking a course like combinatorics, which is essentially discrete math 2, quite often it's going to be acceptable to leave this as 2 to the 6th. For now, let's go ahead and calculate the answer to be 64. Here, the answer would be 2 to the 5th, which is 32, plus 32 minus 2 to the 4th, which is 16. So there are 48 options. Let's take a look at our last question. How many bit strings of length n are there, not counting the empty string? So let's go back up to our initial question. It says, how many bit strings of length 6 are there? That's exactly what this is saying, except it's giving me n instead of 6. Well, I know that the solution here was 2 to the 6th. So it would make sense how many bit strings of length n are there would be 2 to the n, because there would be n different spaces, and each one would have 2 choices. Now, what happens here is it says not counting the empty string. And the empty string is just the string that is all zeros. And there's only one of those. So all I have to do is take 2 to the n and then subtract the one empty string. So 2 to the n minus 1.
So let's take a look at Douglas County, Nebraska, which is where Omaha resides. Have license plates that begin with 3 letters and end with 3 digits. How many unique license plates are there in Douglas County? So there are 6 items, and the first 3 can all be a letter, and there are 26 letters. And the last 3 are all digits. There are 10 digits. And so all we would have to do is multiply all of that out, which is 17,576,000 different options. So what if those were still the license plate restrictions, but a 0 is no longer allowed as the first of the 3 digits? So I can't use a 0 here. So what's going to change? Well, now there's only 9 here. So how's that going to change my solution? If I take 26 to the 3rd times 10 squared times 9, because there's now only 9 options for this digit, I get 15,818,400 different license plates.
Now this question is a bit more abstract. This says use the product rule to show, and again, whenever you see something like this is saying, I want you to prove it to me. Now it doesn't have to be a formal mathematical proof, but it does need to be a proof that shows that it's true for all values. So this says use the product rule to show that the number of different subsets of a finite set S is 2 to the cardinality of S, or 2 to however many elements are in S. So before we look at this in a proof, I want to just show you an example of what they're talking about. So let's say S has 2 elements, 0 and 1. So the cardinality of S is equal to 2 because there's 2 elements. Now, if I'm looking at the number of different subsets, let's just list them. I could have the empty set. I could have the set that includes just the element of 0, a set that includes just the element of 1, or a set that includes 0 and 1, and those are all of my options. Now, according to this, 2 to the cardinality of S should be the total number of subsets. Well, 1, 2, 3, 4, so the cardinality is 4, and that's what this says, 2 to the 2, which is 4. So have I shown this? Have I proved it? No, I've looked at one example. So I've only shown that if S has 2 elements, that there are 4 subsets. Let's take a look at if S has 3 elements, 0, 1, 2. So the cardinality of S is now 3. So according to this, I should have 2 to the 3rd, or 8 subsets. So again, I haven't proved anything. I'm just showing you how to verify it's true for 2 or for 3. So the empty set, 0, 1, 2. So those are all of the elements of all of the sets of size 0 or size 1. Size 2 would be 0, 1, 0, 2, 1, 2, and of size 3 would be 0, 1, 2. Notice there are 8. So again, have I done what they've asked me to do? No, I have not. This is not a valid proof. We were just looking at that to verify that yes, it's true for s is equal to 2, and yes, it's true for s is equal to 3. I now need to generalize that this is true for s is equal to some whatever value s is. So what I'm going to do is I'm going to take you through how I would write the proof, but I'm not going to write the proof myself. I'm just going to say what I would write in words. If we have the number, or if we have s elements in a set, total of s elements, then I can say that for each element in the set, the element is either in the subset or not in the subset. So for my first element, it's either in or out, so that's 2 choices. For my second element, it's either in the subset or out. That's 2 choices. For my third element, it's either in the subset or not. And you can see exactly what happens here. This looks very similar to our bit string question. So what I have here is 2 to the cardinality of s. And again, how would I explain that? Because each element is either in the subset or not in the subset. So there are 2 choices for each element.
This question actually is just a really straightforward product rule question, but I wanted to throw it in there because we haven't talked much about Cartesian products. We introduced them several sections ago, and we will get into them when we talk about relations. But essentially we're saying, let's say if of set 1, basically A1, has 7 elements, and the number of elements in A2 is 4, how many elements are in the Cartesian product of A1 by A2? So essentially what we're saying is, and I've given you an example, we don't have to do the example, but essentially what we're saying is I could have elements or ordered pairs that start with 1 because I'm using the first digit or the first value from set A1. And so my choices there are to use 0, 1, 3, and 7. And so that's the ordered pairs using 1. And I could do the same using 2. And so 2 could be the first element of the set. Again, moving on to the next element of A1. And in A2, I'm choosing 0, 1, 3, or 7. And you can see that this is going to be pretty straightforward because there are 7 elements in set A1. And each time I choose a new element, there are 4 different ways to write that ordered pair because I have to choose each element once. So this is really just 7 times 4, or 28 different ordered pairs. So we don't have to write them all out to get the idea, but again, this is just a product rule question. Our next question has to do with computer passwords, and we're saying the computer password can be 5 to 6 characters. The password must contain at least 1 digit, and all other characters must either be digits or lowercase letters. How many unique passwords exist? So in this case, you might be tempted to find all of the different ways that you could have a 5-character password and add them together, and then find all of the different ways that you could find a 6-character password and add them together. But it might be easier to sort of look at the opposite problem, which we do quite often when we're dealing with combinatorics. So what I would start with here is I would say all of the possibilities. So I'm going to start with passwords with 5 characters. All of the possibilities, including that they all have 1 digit, is that I have 36 options because there are 10 digits and 26 letters. So there are 36 options and I have 5 of them. So that would be all of the different ways that I could use either a digit or a letter. But it says it must contain at least 1 digit. So what I want to do is essentially get rid of any of the options that don't have any digits. And the options that don't have any digits would be 26 to the 5th. And so that's really going to be my answer. And I can, of course, compute that in my calculator. And I come up with 48584800. So that's the number of options of 5 characters. Well, now I want to do the same thing for 6 characters. So for 6 characters, it's 36 to the 6th minus 26 to the 6th. So again, I'm using the same concept that says, hey, because it's at least one digit, I'm just going to get rid of all of the options that don't have any digits. And again, I'm just going to use my calculator to find that difference. I'm replacing the 5 and the exponent with a 6, and I'm finding my answer, which happens to be 18678665660. And now I'm going to use the addition rule. And the addition rule says, because I've got these two options, I can then add together the two solutions that I had. And what is the total? My total number of options, 19164511360. And we can see we have a very, very large number of possible passwords. So let's take a look at a couple of more difficult questions, or I guess more difficult depending on if you love combinatorics or don't. But here we're looking at the number of ways a photographer at a wedding party can arrange the groom, bride, and all 6 members of the wedding party if the bride and groom must be next to one another. So the way that I like to think about this is, yes, I have 8 people, right? I have 8 people that I have to place in 8 positions. However, because again, we're just lining up 8 in a row, but I know that the bride and the groom must be next to one another. So really, I'm going to think of this as 7 groups, because each person is a group, and then of course my bride and groom group. So I've got 1, 2, 3, 4, 5, 6, which are members of the wedding party, and then I've got a group that is bridegroom. So that means in the first position, I've got 7 different options. So I can either choose to place the bridegroom or one of the members of the wedding party. And then my next position, I have 6, the next I have 5, the next I have 4, 3, 2, 1. We get the idea. This is just 7 factorial, right? So the only thing missing from this solution is that I also have the bride and groom, and it didn't specify in the question which side the bride should be on or the groom should be on. And so I have to take this times 2, because it could be that the bride was to the left and the groom was to the right, or vice versa. So I'm going to take 2 times 7 factorial, and that's going to give me my solution. That final solution is 10,080. So now that we've done that one, if you want a challenge, see if you can do the next question dealing with the same situation. If you want to, go ahead and press pause and try that question. Otherwise, let's go through it together. Here we're saying we still have the 8 people, but we want the people who walked together, so each couple of the wedding party, we want them to be next to one another. And we want the bride and groom to stand next to one another as well, obviously. And we want the bride to be to the left of the groom. So again, I still have 8 people, but really I've got my first couple, which includes person 1 and 2, my second couple, 3 and 4, my third couple, 5 and 6, and then my last couple where we want the bride to the left of the groom. So really I only have 4 options, so it's 4 factorial. This guy is already set in the correct order because it's bride groom. These guys can be in either order, so that's 2 options. These guys can be in either order, so that's 2 options, and these guys in either order, which is 2 options. So my final answer is actually 4 times 2, or 4 factorial times 2 to the 3rd. And that solution is 192 different ways. So we have 2 more questions to try. The first one is pretty difficult, and the second one is a little bit easier. but still difficult. So I saved the hardest for last. So first let's look at how many 4 permutations of the positive integers not exceeding 100 contain 3 consecutive integers in the correct order in consecutive positions in the permutation. Woo! So what does that even mean? That means I have 4, it's a 4 permutation, okay? And permutation means the order makes a difference. So I'm looking at this and I'm saying, okay, I've got 4 items, and my question is, if I've got a set of 3 consecutive integers, so I'm talking 1, 2, 3, or 2, 3, 4, or 3, 4, 5, blah, 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 up to 98, 99, 100. So there's a bunch of them, right? How many of them are there? There are 98 different ways that this could happen. 98 ways. Okay? Then, after I've used 3 of those 100 digits, there are 97 digits left to go on the extra space. So I'm either putting my 3 digits here, and then there's 97 digits that could go there, or I'm putting my 3 digits that are consecutive here with 97 possible digits that could go on the first position. So again, we can see that there's 2 ways that this could happen. So you might think we're done, but there's this one extra thing we haven't looked at yet, and that is what happens when I have all 4 numbers in a row. What happened? I actually counted it twice because I counted it as the 1, 2, 3, and I counted it as the 2, 3, 4. And how many times did I count it twice? I counted it twice 97 times. So this is how I will figure out my final solution. 2 times 98 times 97, and then take away the 97 I counted 2 times, and I end up with 18,915 different ways that that could happen. So there's a lot going on. Yes, it's difficult. It's an acquired skill where the more you do this, the more those kinds of things will come to you. Now let's look at, if the math faculty of a large university consists of 5 men and 6 women, how many committees of size 4 can be formed if the committee must contain at least 1 member of each gender? So you might be tempted again to try to figure out all of the different ways that this could happen, but the best way to go about this is, I know total, again we're looking at combinations because permutations means the order matters. This is a committee, and so this is a combination. And I have 11 people total, and I'm choosing 4. So that would be the total number of ways that I could come up with a committee. But I need to have at least 1 of each gender. So what I'm going to do is I'm actually going to take away all of the committees that consist of only women and all of the committees that consist of only men. So I'm going to take away the combination 6 choose 4, which means out of the 6 women, I chose 4 of the women. And I'm going to take away the combination of 5 choose 4, meaning I have 5 men and I chose 4 of the men. And if I do that, then I've taken away all of the ones that have only men and all of the ones that have only women. I underlined them in the wrong order. Sorry about that. And what I'm left with is all of the committees that have at least 1 of each. And so I'm just going to utilize my calculator again to find my solution. And that solution ends up being 310 different ways.
Let's finish up with 2 questions dealing with diagonals. So for the first, how many diagonals does a convex hexagon have? So obviously I've already drawn in your hexagon. And we can just do this by brute force. My first vertex has 1, 2, 3 diagonals. My second vertex has 1, 2, 3 diagonals. My third vertex has 1, 2, 3 diagonals, but of course I've already counted one of those once. But we can see that the pattern here is that there are 3, diagonals at each, and then of course that we're recounting some. So let's continue. So far I'm just going to put next to this that I've counted 1 more than once. And then let's do purple. So I've got 1, 2, that one's already been counted, 3, that one's already been counted, so I have 3, but 2 have already been counted. Alright, I'm running out of colors, but we'll just go with it. This guy right here, I've got 1 that was already counted, 2 that was already counted, 3 that was already counted, so I have 3, but 3 were already counted. And then of course the same thing is going to happen to my last one. Purple again is fine. I'm going to have 3, but 1, 2, 3 were already counted. So essentially what I'm saying is if I needed to add these up, I would have 3 plus 3 plus 3 plus 3 6 times. But then I would take away 1 plus 2 plus 3 plus 3. I would take away all of the ones that happened that were counted more than once. So 3 6 times is 6 times 3 or 18. And then I'm going to subtract 1 plus 2, which is 3, plus 3, which is 6, plus 3, which is 9. So 18 minus 9 gives me 9 total diagonals. So why did I do it that way? It seems kind of silly, but I wanted to kind of think about it in the same way that I would look at for a more general case. Because obviously a hexagon has 6 sides and we can count those up very easily. If we're looking at an n-gon, then we have n sides. So let's take a look back at how I might do this. This had, and I'm just going to erase all of our hard work to make it easier. When I drew in this one, I knew that I could have 1, 2, 3 different diagonals. And I knew it was 3 because it couldn't go to itself. You can't draw a diagonal to itself. And you can't draw a diagonal to the 2 adjacent points. So it's always going to be n minus 3. So in this case, because it was 6, 6 minus 3 is 3. That's why I wrote a 3 for each vertex. Which means all of these will be n minus 3. And again, n minus 3 would represent the value that I found here. So how many diagonals does it have? So far, I have n minus 3. How many times do I have n minus 3? Well, 1, 2, 3, 4, 5, 6. That was how many sides does it have, or how many vertices does it have, which happens to be the same value. So to find the value on the top, that would be n times n minus 3. N because that's the number of vertices, and n minus 3 because that's the number of diagonals that you can draw from each vertex. Now, how do I know how to get from this value to this value? Well, what I'm looking at is that each vertex is going to end up counting the same diagonal twice. It's going to count it once coming out of that vertex, and then once coming back into that vertex from a different vertex. So essentially, I'm taking n times n minus 3 and dividing it by 2. So would that work for the convex hexagon that we just looked at? Could I take 6 times 6 minus 3 divided by 2, or 6 times 3 divided by 2, which is 18 divided by 2, which is 9? Yes, I could. Now, I could do many more examples to show or verify that my solution makes sense, but this, in fact, would be my formula. Up next, we're going to take a look at the binomial theorem.